working on stream channel restoration. Rebecca is a water resource engineer with Wenck Associates. She has 20 years of experience. She works out of Minneapolis. And she's not only a principal engineer with Wenck, she's also a watershed district engineer for multiple ag watersheds in Minnesota, covering 1,500 square miles. So, welcome, Rebecca.
Thank you. So, across Minnesota, as I imagine across Iowa, drainage ditches are a common sight. We have a lot of agriculture, just like we do here in Iowa. A lot of these drainage ditches we see in the late summer, they kind of become almost like linear stormwater ponds. They're kind of stagnant because they're wider than they're supposed to be, than a natural stream would be to accommodate drainage. And they're deeper than they're supposed to be, so then they would be naturally to accommodate drainage. So in Minnesota, this becomes an issue for us because many of our streams are also public waters. So this means they actually need to meet water quality standards determined by the NPCA, Minnesota Pollution Control Agency. So when we have drainage ditches that are also streams, we have that are over-widened and deeper than they need to be. This creates a lot of issues for water quality and habitats. I'm going to give you an example of one project in Minnesota that we did where we had some pretty interesting results using basically just a design for the hydrology rather than a lot of pools and riffles, things that we typically think of as habitat. So let's talk about just the background of this watershed, and this is the map I put up first rather than a different map, but this is about 160 square mile watershed right in the middle of Minnesota. If you head west out of Minneapolis, about an hour, you'll get to the Clearwater River Watershed District. The green is soybeans and the orange is corn. So you can see the density of agriculture in this watershed, and that doesn't really include other cropland or pastures. There's also a lot of blue on the map. These are all recreational lakes, high-value recreational lakes, where we have a lot of tourism. And this is the Clearwater River. So you can see there's a lot of these little lakes along the Clearwater River, directly downstream of a lot of agricultural areas. So we're in Iowa, we have kind of that urban agricultural clash. We have that in Minneapolis and Minnesota too, but we also have kind of that lakeshore owner urban or lakeshore owner agricultural, that constant kind of battle between the two. And in this watershed, we really tried to use some unique approaches to bridge that gap and get everybody working together. So here's a different map of the watershed that just kind of shows the waterways. Again, these are all green. These lakes are all green. Green means that they're impaired. They're impaired because they have too high phosphorus concentration in the summer. We get algae blooms, and they exceed the state standard. So that means we have a hard time using the lakes for their intended purposes. It makes it hard to fish or swim. The Clearwater River is also a funny color here. It's red. It's impaired because it doesn't have enough oxygen to support the ecosystem, or to support the ecosystem that we would expect to see in a natural stream here. This portion of the Clearwater River is also County Ditch 44 for Meeker County. So it's not only drainage, but it's a natural stream. So, actually go back again. This is the project area that I'm talking about, is a restoration of a 500-acre wetland complex adjacent to the Clearwater River. So it's the interaction between the river and the wetland that was causing a major component water quality problems. And just to kind of set up the issue, this impairment that was documented along the Clearwater River, we did a study back in 2003. Collected a lot of data, we did a qual-2K model, and identified the causes of the problem. The first thing that we found out is that our dissolved oxygen impairment was only an issue downstream of this 500-acre wetland complex. We didn't have dissolved oxygen problems in the upper portion. there was a question of what's happening here, what's going on here that's potentially causing the issue. So based on water quality data that we collected, we figured out that there was a lot of soluble phosphorus being released from that wetland during the late summer. There was also a lot of oxygen demand within that wetland, a lot of sediment oxygen demand. That was about half the cause of our dissolved oxygen problem. The other issue is just a lack of reaeration for this stretch of the river, because it's very, 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 very flat, 0.04% grade. We have no drops. When we're talking about river restorations, we usually think of places where we have a little bit more grade, where we're putting in control structures, we're putting in, we're putting in pools and riffles. We hardly had any fall to work with, so the question is, how do we restore water quality here? How do we restore habitat? This wetland though was also trapping particulate phosphorus in the early spring and summer. So there's some benefit to the way the system was operating that was protecting the downstream lakes from particulate phosphorus from high flows. But there was also a detriment to the lakes downstream because there was a lot of soluble phosphorus being released, causing algae blooms in Lake Betsy and these other downstream lakes. So how do we balance, and then that on top of the dissolved oxygen issue. So how do we balance a solution for this system that tries to maintain the assimilative capacity for particulate phosphorus, yet limits the ability to transport the soluble phosphorus, and solves your dissolved oxygen problem and your habitat problems and protects all the lakes. So when we wrote the studies, I actually thought, well, that's not going to happen. We're going to get one or the other. We're going to get the stream or the lake water quality. But as we collected some more additional data, came up with a conceptual idea. And we got a grant to see if the idea, to collect more data to see if the idea would work. So here's an aerial photo of this wetland. You can kind of see here's the Clearwater River coming through. There's a major change in slope from here to here. You can see that's some of the tributaries coming through. And you can see the section is really ditched and really straight. And you can see there's water standing in there, but that wasn't the major flow path for the ditch, what we identified. While there was water flowing through there, it was only going through that main section during really high flows. Most of the time, the water meandered through this 500-acre wetland and then rejoined the main channel here. So this wasn't necessarily even a stream, it wasn't even a functioning ditch because we had all the sediment that had accumulated here in a ditch that hadn't been used in 100 years. And so basically the channel had silted in and the flow was going through here. So you had really low flows going through this major wetland complex and pegging the dissolved oxygen all the way down to Lake Betsy, which is over here. So I've got a couple photos. This is at the downstream end looking upstream at this section. This is pretty much what this section of the river always looked like. It was always pretty much covered with algae and pretty stagnant. This is pre-project. This is the same bridge looking downstream. Wasn't really inviting. The habitat scores were abysmal. Dissolved oxygen was 0 often. Phosphorus was high. Here's the upstream end of the water. Again, there's a lot of duckweed in there too, but again, just really low dissolved oxygen, not as bad at the upstream end, but really poor water quality, lots of phosphorus. So this is kind of that central portion where you can see there was a lot of sediment. So we had standing water in the area, but we just had a lot of sediment that had accumulated. Not much for habitat. And just another air photo so you can kind of get a sense of the scale of that wetland. The Clearwater River, you see it's pretty, you can kind of tell the slope change or the grade change. You have a nice meandering river here. You can see that meander belt, and then all of a sudden it's just straight. Goes into the Clearwater River. So this is the area that we restored. So rather than the river kind of coming through here, we took it through here. So this is just the natural flow path with all of the tributaries, and we did some dive studies to kind of just look at what was happening here. So this is an example, or this is a kind of an overlay of that system with the repair, or with the design. So you can see it's a re-meandered channel. And you can see the meander belt is a little different. It's a little, the amplitude is smaller here because it was even flatter here than it was here. So the design of the channel was actually more important for water quality than I think that the meander belt. Typically we think, oh, meander streams are healthy streams. Well, it wasn't necessarily the case here. What was really the issue is that we had a very, very large channel for a very, very small base flow. And really the drainage ditch in that area wasn't draining that 500-acre wetland. It wasn't ever, it was never successful at making that cropland. It was occasionally hayable, but not very often. So we weren't really giving up any drainage benefits for the landowners, but we had an opportunity here. So what we did was, rather than have that channel go through the wetland, we thought, well, what if this functioned more like a channel with a riparian wetland that was seasonally flooded for high flows? So what we ended up with was essentially a 3-stage ditch. So this little notch would carry the base flow, which we had a base flow of groundwater, which has actually increased over the years because of the tile drainage. Then we had a smaller channel for the 2-year design. And then we have the 500-acre wetland, which accommodates the larger flows. I'm gonna go back for a second. So we definitely have spillage into that 500-acre wetland here. We also have a diversion where we utilized part of this upstream section as a sediment basin, so we're not, we wanted to have some ability to maintain this, so we're not just clogging the wetland with sediment. So we do have a small sediment basin here. I've already cleaned that out twice. So the interesting thing about this notch, and I learned this from a couple of different drainage projects that we have, is that you don't necessarily have to construct that. I don't have to have someone with a backhoe out digging this tiny little meander within my meander 2-year event channel. That this will kind of naturally form and cut itself, and it's actually a kind of a pretty picture, which I couldn't find, but take my word for it. That's what it looks like. So got some photos of the construction. We did winter construction. We waited until things froze up. When we're working in wetland, the soils are not great, so we had anticipated we would need a lot of mats for construction and have difficulty with access, but we actually had a pretty easy time. So this is a photo of that channel. This was that former ditch channel that on air photos would occasionally during high flows it would fill up with water. In air photos it would look like it was always full of water. But in reality it had a lot of tree stumps. It looks like a very, very poorly maintained drainage system. But we had a conservation crew come in and help us with the clear cutting. That was a pretty big expense. You can see here's kind of some of the redness of that water after they started to clear out the trees. And we started to clear that path. And just some additional pre-construction photos of the channel. So the wetland would be over here, and there are low areas along the whole channel where those high flows can access the floodplain. And then the slopes on the other side of the bank, the north side of the bank, are very steep, so it's really forcing it to get into that riparian wetland. So this is closer to the downstream end. While they were constructing, this is a larger amplitude of the channel. This is the wetland. So we do have some of those high flows going into the wetlands, and we also constructed a limestone filter berm to try to take out some of that soluble phosphorus. When we came in this talk before, I've had a lot of people really get excited about the limestone soluble phosphorus. You get a precipitate of the phosphorus coming out with the carbonate. And a lot of people are kind of putting these in, and I don't know that the science is really supporting how they're used. But we had, it was more just for testing. I really am not able to partition out the impact of this versus the channel, but just based on flow regime and how often that flow is accessing that wetland. My working theory is that the channel shape itself has the biggest impact on water quality and on the habitat improvements that we saw. So again, we did for a regular ditch project, we wouldn't use, straw or blanket, but we had a little bit more erosion control here. So we have results. And we have a district administrator who is in front of an airplane, so we can take some cool pictures. But you can kind of see the meander belt here. Here's the 500-acre wetland. You can see there's kind of pockets where it's higher and a little wooded, and then there's areas for access. This is the old flow path. There's the filter dome. This is the downstream end. So this channel essentially used to only have high flows, and all the low flows went here. We flipped them. Now this was carrying kind of the low flow, the base flow of the 2-year event, and this channel the wetland would accommodate the higher flows. Here's another air photo. You can kind of see some of our draws coming in here. So, I don't know if you remember the photo I showed you at the beginning. I said this is the downstream end. This is the downstream end post-construction. No more green, slimy stuff. And then every summer since we, even before we had final stabilization, no green, slimy stuff. So just the photo, I think, has been very compelling to me. When the staff member from the watershed district called the first couple times he had gone out monitoring, he's like, sent me these pictures, like, there's no green stuff. So he said, well, it's from our project. I said, well, we can't say that yet, but after sustained no green stuff and the rest of the data I'm about to show you, I'm pretty sure it's from the project. So, because we're engineers here, some of us are engineers, we have such ugly figures. So here's one of my ugly graphs. We have pre-construction dissolved oxygen and post-construction dissolved oxygen. There's the construction. This is upstream of the wetland and downstream of the wetland. So as you can see, no dissolved oxygen issues upstream of the wetland. We definitely had consumption of oxygen from upstream to downstream. Here is our state standard of 5 milligrams per liter. So post-project, we still have some oxygen demand within that area, so we still have some sediment oxygen demand. And the other thing is that channel is really, really flat right there, so we just have a limited amount of reaeration. But we improved reaeration with the project by increasing velocities. So definitely above the state standard after, of course we'd love to have, 5 years or more data to show you, but this is what we've got so far. And some pretty pictures. So this is the reason that the wetland never drained, aside from just being very flat, is that there was a downstream control. So it's a tailwater controlled structure, or tailwater controlled system, but the Department of Natural Resources there still made us put in a grade control structure so we wouldn't drain the wetland, even though in 100 years of ditching, no one had been able to drain that wetland. We were somehow imbued with the powers to have to do that, but it made us a pretty picture. So that's looking downstream. The other thing I want to point out is kind of, we had a lot of green canary grass, and while the post-project riparian vegetation was still a lot of green canary, by disturbing that seed bank, and I've heard anecdotally that in other areas where you disturb the seed bank, if you go in there with a backhoe or whatever earth moving equipment, we tend to stir up the natural seed bank. So we've seen some of the native plant species come back, but we haven't had a budget to really do a surveillance. So I'd love to kind of have documented that a little bit better. So here's another kind of ugly little graph, but it's not. I'll walk you through it. We've got dissolved oxygen again, and this looks at dissolved oxygen before and after the project, and it looks at it across all the flow regimes. So it kind of goes to it talks about our why we designed the channel the way we did. So the black dots are pre-project, and you can see in high flow we had dissolved oxygen levels. Here's the state standard. Everything below that red line is a violation. So lots of violations in very high flow, lots of variations in high flow, lots of variations in mid flow, lots of variations in low flow, and very low flow. So post-project are the green dots. So we still had one very high DO violation, and we'd expect that because we've got sediment oxygen demand from that wetland still. So when we've got water accessing the floodplain and getting into the wetland, we have some sediment oxygen demand. But the rest of the time, unless we get into really low flow, where it's really slow, we did a lot better. So there's just another photo. You can kind of see some of the, see some beautiful reed canary grass. So phosphorus, I talked about at the beginning that we were looking at dissolved oxygen. We are also looking at phosphorus. So this is total phosphorus before and after the project, upstream and downstream. Oops. So we have phosphorus on the left here. So 100 is the stream standard for this area in Minnesota. So upstream, still very high, much higher than the stream standard. Keep in mind we've got about 80% agricultural land use upstream. But downstream of the wetland, our average total phosphorus is high. Same in 2011. So we hadn't had site stabilization totally yet, but closer. And then we haven't had any increase in the last 2 years. And this is compelling, but it's not the most compelling. To me, it's not the most compelling piece. It's another photo. So just really throughout the channel, we've had, it's visually a much prettier system. And this is a little higher flow, so you don't see the notch, but within this kind of 2-year belt, there's even a lower flow channel that kind of cut itself out. So this is total phosphorus, but it's seasonally. And the reason that we want to look at it seasonally is because we tend to have peaks in soluble phosphorus later in the summer. So again, the black is pre-project. It starts in January, ends in December. So this is kind of your late summer where we would expect to have really big peaks at the downstream end of that wetland. This is where we would expect to monitor and measure and see our peaks in soluble. So this is when that wetland was exporting. The green dots are post-project. So we really eliminated that huge spike that was causing algae blooms downstream. So here's soluble phosphorus. Again, we look at both and kind of just make sure, again, we would have high phosphorus. And by high phosphorus, as high as 600 micrograms per liter. That's 10 times the state standard for shallow lakes. It's really, 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 really high phosphorus. And we're still high, but here's because that state standard, we really eliminate that peak. We definitely still have some, but we eliminate these really high exports that were causing these downstream algae blooms. So one of the really exciting things that came out of this project, and again, we kind of came up with a conceptual project that based on the data we collected and the modeling we did, we thought, well, this should work. But as an engineer, if you've ever designed something, you kind of do a little prayer before it goes in and you start collecting data and just, I don't know what this is going to do. Let's see what it does. So we wanted to see what it would do to the habitat before and after. So we went out right into the before and we collected habitat data. So the Hilsenhoff Biotic Index was 8.2. In slight golf, where lower is better. So 5.8 is the best achievable Hilsenhoff Biotic Index score for this ecoregion. Between pre-project and post-project, we're down to 6.1. So that was a pretty big improvement. The amount of intolerant species we had 0 before project went up to 1.6. Pollution tolerant species dropped from 35% down to about 19%. Super tolerant species went from 56% down to 6%. So that means these are the little guys that can survive pretty much anything. They're like the Twinkies of macroinvertebrates, right? So the spam of macroinvertebrates, they can just survive in any setting. So these little guys were doing as well as some of the less tolerant species. So that was a really exciting thing. So we also talked about lake blooms, algae blooms, right? So Lake Betsy is this tiny little lake, this itty bitty little tiny little 180 acre lake downstream of like an 80 square mile agricultural watershed. And so this data kind of takes us back to 91, because I want to show you this. There's a bigger picture than just this work that we're doing down here. But back in the 80s, actually the founder of Wenck, Mr. Wenck, did some projects in this watershed. They're both capital projects and programs that dramatically improved water quality. It kind of brought it down to pretty much a fairly consistent level over the last 30 or so years. But we were still inferior. We were still above the state standards. We pushed about state standards 60 for the snakes and the shallow lake. But these are the three readings that we've had post-project. So I'd like to see more data before I start doing trends, but we've seen a pretty significant improvement. It will tell you, though, we've done other projects, other programs in this watershed. It's been a target area. So, but just based on the data that we've collected tonight in the wetland, I would say that this, and then we did a targeted fertilizer application program. We had 70% uptake in the watershed. So I think kind of that 1-2 punch combination really has done a lot to improve water quality. Well, there was a last slide with my information on it, but keep it a customer button. Does anyone have any questions? So the question was, what was the process that caused the reduction in the phosphorus? Before the project, all of the flora, most of the flow was going through the wetland, and there was sediment oxygen demand and exportable soluble phosphorus from that wetland. So you have 500-acre wetland exerting oxygen demand and kicking out soluble phosphorus. So that pre-project, you had all that soluble phosphorus heading down. But that wetland was actually also trapping particulate, so there was about a small net increase usually in the amount of phosphorus we were having from upstream and downstream. So that was the mechanism that was causing the phosphorus increase. So how we reduced it was we said, well, most of our flow, the low flows, we can fit into this little tiny channel. Let's put them in the channel and just use the riparian wetland as access to the floodplain. So that really just changing that flow regime and designing a channel that accommodated base flow and accommodated the 2-year. It was just it's a hydrology solution. Yes.
Were there permits removed as a result of the project?
So you need a certain amount of data. It's kind of like a weight of evidence. So we've had 3 years and probably 1 or 2 more years of data, and hopefully be able to remove the dissolved oxygen impairment. I'm skeptical about whether we can actually remove the impairment on Lake Betsy. The reason for that is it's a teeny tiny little lake where the residence time is on the order of days in the early spring. So if you have a large drainage area and a river with a standard of 100 flying through a teeny tiny little lake with not very much similar capacity, I think that 100 is about what we're going to get to in Lake Betsy. I think that's the best achievable concentration. And we're at like 135 right now. So I think we're very close to what's achievable. I don't know that we'll meet the standard there. Anyone else? Yes, sir.
I was just going to mention your close pictures were really nice. I had that in my backyard. I was just going to point out the way I think those previous speakers were not appreciating that. The difference in channel restoration. With the downside, you're actually using to create that pond channel. I know in Iowa there's some stream systems where after the downside, churn out to the lakes and sediments that have considerable amounts in some places with particular phosphorus. If you see the map where maybe there was an upswing where you had some of that downsetting early in the restoration, and then it's taken off later on.
Yeah, so the question was, did we see, because our design actually incorporated the use of some natural channel processes to create the whole channel, did we see an uprising or did we see an increase in sediment that, before we had the channel stabilized? And yes, the answer was absolutely we did. We measured it was a very slight, like a 5% increase in TSS, downstream to upstream. That was after the first year, but we didn't see a correlating increase in phosphorus. So we assumed it was mostly the channel. The banks aren't completely established yet. It was usually just in high spring. But we did have a pretty nice, vegetative restoration.
Because you have all the floodplain, so that's probably settling out some of
Yeah.
it. We did have
Yeah.
the downstream. Okay. Thank you.
Anyone else? Yes, sir?
With your low grade in the channel, I'm curious why you guys use the grade pattern with high viscosity if you want to keep low velocity or
So So the question is, and I love your question, I'm going to just respond to it in a second. The question was, why did we add, if we were trying to increase the velocity, why did we add a remeander? And my answer to you is the DNR made us because they didn't get the whole velocity issue. So we had that argument back and forth, that they really wanted to have that, but we still have high dissolve option. I wonder if we had used the original design was straight. We all think of that meander channel as kind of that natural condition, but from that value engineering, what we were trying to achieve from a water quality standpoint, we couldn't justify the additional cost. But again, the regulatory agency, and we work in really close partnership with, we brought in all the local and state and federal regulatory agencies. Let's talk about the plan, let's look at it. And that was their input, and they were not willing to budge on it.
So that was excavated with your excavation, right? I thought you mentioned that sometimes it was self-formed in the area
So he asked if which part of the channel self-formed. Part of the channel did self-form, and we'll go back to the channel that you saw in the air photo. That's the 2-year channel. That was about the 2-year. So the base flow channel, and I'll show you just that cross section. The base flow channel is the cut. That's that 2-year channel that we did excavate. If there was no water in here, you'd see a meandering channel that cut in here. That was just baseball. Just that little notch. So the channel design on the plans and specs. So the channel design on the plans and specs was just this. This was a little volunteer.